Okay, this is the video on classification of matter. And let me just get my tools ready. Okay, so when we're talking about matter, matter is anything that has mass and takes up space, right? And all matter is made up of atoms, and atoms are the smallest particle of matter, right? So when we look out into space, and when you see just the black part, usually that black part is just called a vacuum. And by vacuum, we mean that there are no atoms present at all. It's just space, right? But when you're looking at the planets or the stars or the galaxies or nebulas, they're made up of atoms. And that's what matter is, right? Now, any sample of matter that has a fixed composition is called a pure substance, right? And by fixed composition, we mean that it is going to be always the same, no matter what sample of that substance that you look at, it'll always be exactly the same. For instance, if you look at copper wire, pure copper wire, then any sample of pure copper wire you look at, it will always be made up of only copper atoms. Right? Or if you look at a sample of dry ice is frozen carbon dioxide, right? And so any sample of dry ice you get, it's always going to be exactly the same, made up of one carbon to every two oxygen atoms, right? Now, a pure substance, it can be either an element or a compound, right? And so elements are substances in which all the atoms are the same. So it doesn't matter what sample you get of it, all the atoms are going to be the same type of atoms. For instance, if you look at a sample of pure gold, all the atoms within that pure gold would be gold atoms. Now, atoms then can also be defined as the smallest particle of an element that still retains the properties of that element. For example, here you see a photograph of silicon atoms. Now, we can't see silicon atoms with our eyes, but we can see them with an electron microscope. Now, these aren't the microscopes that you have in biology class. These are very special microscopes, right? But they're able to magnify it small enough or large enough so that you can see individual atoms, right? This is a sample of silicon, and this sample would be made up of trillions and trillions of silicon atoms, but all the atoms would be exactly the same. Right? And there are 92 different natural elements found on Earth, right? And so on the periodic table, it lists all the elements that we know of, right? And so if you count all the way down through, this is called the atomic number, this 1, 2, 3, 4, count all the way down to 92, you end up with uranium, right? So all the atoms or elements that are smaller than uranium, they're all natural made. And by that we mean they're made through natural means. And so they're made within stars. And we'll learn about that a little bit later when we study nuclear reactions, right? So elements that are larger than 92, so you see some here and you see some here. Those are synthetic. They're man-made. They're made in labs. And they do that by bombarding atoms against each other. And they stick together and form a new type of atom. And sometimes they only last a few seconds, such as these ones. But sometimes they last a little bit longer, like americium, which is an element you find in the smoke alarms. I know all elements on the periodic table are represented by what's called a chemical symbol, right? So that means that they'll have a capital letter and sometimes a lowercase letter with it. Now they'll have a lowercase letter with it when the other capital letter's already been used for another element. For example, hydrogen is atomic number 1, and so it uses the capital letter H. But helium, atomic number 2, also uses an H, but then it uses a lowercase e to separate it from hydrogen and helium. Same thing happens for phosphorus, which is P, and lead, which is Pb. Right now, chemical symbols are based on their Latin names, not their English names. And so that's why this is lead, and that may not make sense to you unless you know that the Latin name for lead is plumbum. And it's called plumbum after plumbing because Rome, who used Latin, the Romans, used lead pipes in their plumbing. All right, so compounds. Elements, remember, where atoms were all the same. Compounds are when two or more different elements chemically combine during a chemical reaction to form a compound. Right, so an example of a good compound is sodium chloride. It's made up of sodium atoms chemically combined to chlorine atoms. Right, and it takes a chemical reaction for that to take place. Right, once they're chemically combined, we end up with regular table salt. Chemical name is sodium chloride, but we commonly just call it table salt. Right, now all chemical compounds are distinguished by a chemical formula. Right, and this chemical formula is a ratio between the atoms within that substance. So for like pure aspirin, for every 9 carbon atoms, there are 8 hydrogen atoms and 4 oxygen atoms. Okay, and so in examples like on quizzes and tests, you'll be asked like which one is an element. So where you would go, look on the periodic table, and see if it's on there. Also, look to see if it has a chemical symbol. Then you know that it's an element. For a compound, it'll give you a chemical formula. And that's how you know it's a compound. Right now, one thing about compounds is that once they're chemically combined, the properties of the different elements are different than the properties of the compound. For example, sodium is a poisonous metal. When you place it in water, it ignites and explodes. Chlorine is a poisonous gas that they use like during wartime when they would throw out gas bombs and kill a bunch of soldiers all at once. Um, that would be chlorine gas that they'd be using. Right, so individually, these atoms are poisonous to us, but once they chemically combine, during that chemical reaction, something happens to these that make them not non-poisonous. And not only non-poisonous, but they actually become essential to life. All animals need sodium chloride for our muscles and our nerves to work. Right, because chemical compounds are chemically combined, the only way we can separate them back into the individual elements is through a chemical reaction. So, for example, if we want chlorine gas, which they use in industries for various reasons, so this is a factory where they create chlorine gas. What they do is they take sodium chloride, dissolve it in water, right, and then they add electricity, and that creates a chemical reaction that separates the water into hydrogen and hydroxide, the OH. And that OH will chemically combine with the sodium to form sodium hydroxide. You end up with hydrogen gas, which they just spin off into the air, and then chlorine gas, which is what they collect and are usually after for industrial reasons. All right, so now mixtures. Mixtures are a combination of two or more substances that are not chemically combined. They're just mixed together. For example, like on this pizza, the mushroom and the olives are mixed together, but they're not chemically combined. Or in a soda, the syrup, the carbon dioxide, and the water are just mixed together, not chemically combined. Right? Because mixtures are not chemically combined, you can separate them just through physical means. For example, this is sulfur with some iron, and just using a magnet, running a magnet through it, can pull out the iron from the sulfur. Or we often separate mixtures just by sifting according to size. That's just a physical change that's going on. Okay, another way that we separate can separate some mixtures is through like evaporation or distillation. So one way that we create salt that we use on our table is they take salt water, put it into a pond, allow the water to evaporate, and collect the salt. Distillation is a way that we can make pure distilled water. Right? So what they do here is they use the difference in boiling points between salt and water. So they take a saltwater mixture, say ocean water, and they boil it. Now the salt won't boil, but the water will. The water will boil fairly easily compared to the salt. So the water boils into steam and it goes through this tube. Now, this is called the condenser tube, and out here in blue is cold water. And that cold water causes that steam to condense into pure distilled water, which they collect in another flask. right? So when we're talking about pure distilled water, we mean that it is pure H2O. There's nothing else combined in it. Um, when you're talking about like water out of your tap, that is fresh water, but it's not pure distilled water. The water out of your tap has chlorine gas in it that would kill any bacteria that might get in the water. It has fluoride in it for our teeth. It has different minerals that were dissolved in it that weren't separated at the water treatment plant, that was already in it when it was in the river and went through the water treatment plant. Okay, so we use distilled water and we'll be using it in class at different times. And they use it a lot in industrial purposes. Okay, so when we're talking about mixtures, there are various types of mixtures. Usually there's two different types, but these mixtures are based on how evenly the substances are mixed together. So sometimes they're mixed together and you can't see the different parts. Other times they're mixed together and you can distinguish the different parts. Okay, now when you cannot distinguish the different parts, it's called a homogeneous or homogeneous mixture. You've heard of homogenized milk. Um, okay, so homogenized mixture, you cannot tell the different part like tea. You cannot tell the difference between the tea, the water, and the sugar that's dissolved inside the tea. Okay, now when it's homogeneous mixtures, another name for them are solutions. Usually refer to a solution when it's a liquid homogeneous mixture. But homogeneous mixtures can be solid liquids or gases. Sometimes you might call these a solution, usually you don't. These solids. All right, but steel is an homogeneous mixture. It's made up of iron, nickel, and chromium that have been melted down together, poured into a mold, and then allowed to solidify. Once it solidifies, you cannot tell the different elements in there. Same thing for bronze, which is copper and tin, or brass, which is copper, zinc, and lead. Air, clean air. Not talking about where the clouds are, because that would you can tell the difference there. That would be a heterogeneous mixture. But this, where it's just clean air, that's a mixture of different elements that aren't chemically combined. Most of it's nitrogen, then at 21% oxygen, and then 1% other gases like water vapor and carbon dioxide. Now, a heterogeneous mixture is when you can tell the different parts. Hetero means different, right? So you might remember from biology, a heterozygote had like a dominant allele and a recessive allele. Right. Okay. So some examples of heterogeneous mixture: sandy water. You can see the sand within the water. You can tell the different parts. Or a salad. You can tell the different parts of a salad. All right. So there's two different special heterogeneous mixtures. One is a solution. Now, I mean a suspension. Right. So a suspension um, is only temporary, and over time it will settle out into different layers. So, for example, like muddy water. Over you let that muddy water set and the mud will settle down to the bottom and then the water will stay up top. Okay, colloid is another special heterogeneous mixture, right? And these contain large enough particles that they don't separate out over time. And what's really cool about them is that they will diffract light. When you shine light into them, they'll scatter the light, and so you can actually see the light beam within them. And that scattering of light is called the Tyndall effect. You've seen the Tyndall effect a lot of times in your life. You probably just didn't know it's called the Tyndall effect, right? So anytime you've seen light beams, sunbeams, that's the Tyndall effect. Fog lights are the best example of the Tyndall effect. When you see the light, like you turn the car and you see the light beams follow as you turn, that's the Tyndall effect. You can also see it in smoke. So one demonstration I always do in class when I teach this is I light a piece of paper on fire and shine a laser beam through it, and you can see the laser beam through the smoke. All right, so from this lesson, this is what the I can statements. You should be able to classify all matter as either a pure substance or a mixture. So remember, a pure substance is when it's a fixed composition, right? It's always going to be the same. So, and a pure substance is made up of an element and or compounds. Right now, a mixture are when things are just mixed together. They're not always the same. Like sometimes you get sweet tea, so different restaurants. Sometimes it's really sweet, sometimes it's not so sweet. Whatever, that would be a mixture, not always the same. Okay, distinguish between elements and compounds. Elements are when atoms are all the same. Compounds are when two or more different elements are chemically combined. Okay, distinguish between a homogeneous mixture and a heterogeneous mixture. Homogeneous mixture is when a mixture that you can't distinguish the various parts of the mixture. Heterogeneous mixture, you can tell the different parts within the mixture. The difference between a suspension and a colloid. Suspension, the particles will settle out over time into layers over time. A colloid, the particles do not settle out and they will scatter light, creating the Tyndall effect. Okay, and that is the end.